Section 6.5, Logarithmic Properties. We're going to take a look at a few important properties of logarithms. The first property is log base b of b equals 1. The reason why this is true is because we know that b to the first power equals b. If I convert b to the first equals b to its logarithmic form, that'd be log base b of b equals 1. The next property is log base b of 1 equals 0. This is true because b to the 0 is always equal to 1 when b is not 0. And b cannot be 0 since our base is positive and not equal to 1. So converting the fact that b to the 0 equals 1 to its logarithmic form, we're given that log base b of 1 equals 0. As for the next one, log base b of b to the x equals x. The reason why this is true is b to what power gives us b to the x? Well, just like the log base 3 of the square root of 3, this question answers itself. B to the x gives us b to the x. So log base b of b to the x will equal x. Next, the last three properties are very useful for simplifying logarithmic equations. The first property, which we're going to refer to as the product rule, is log base b of xy equals log base b of x plus log base b of y. In other words, the log of a product equals the sum of the logs. To illustrate why this is true, let's take a look at log base 2 of 2 squared times 2 cubed. If I multiply two numbers of the same base, I know I would add their exponents. So log base 2 of 2 squared times 2 cubed equals log base 2 of 2 raised to the 2 plus 3. Yes, I could evaluate the 2 plus 3, but I'm going to keep it as 2 plus 3 to kind of just illustrate the point. 2 to what power gives me 2 to the 2 plus 3? That'd be 2 plus 3. On the other hand, what is log base 2 of 2 squared plus log base 2 of 2 cubed? Well, log base 2 of 2 squared would be 2. Log base 2 of 2 cubed would be 3, which is also 2 plus 3. So the reason why we have the property that log base b of xy equals log base b of x plus log base b of y is due to the fact that when we look at the exponential form, when we multiply two numbers of the same base, we add their exponents. Well, logarithms represent exponents. So if I'm taking the log of two numbers multiplied together, I would add their exponents, is essentially what this property is rewording. I also have similar properties for division. Log base b of x over y equals log base b of x minus log base b of y. This rule is referred to as the quotient rule of logs. If we take the log of a quotient, that equals the difference of the logs. The reason why this is true is in exponential form, when we divide two numbers of the same base, we subtract their exponents. And the last rule, log base b of x to the k equals k times log base b of x. So we can take powers that are inside a log and take the power and kick it out as a coefficient of the log. This is true because of the power to a power rule. When I raise a power to another power, I multiply the two powers. Remember, log base b of x does represent a power. The right-hand side just tells me I'm multiplying those powers together. Next, we're going to simplify the following expressions into a single log. Our first expression is 5 log of x minus 4 log of y. The way we simplify our logs into a single log is we want to follow the order of operations in order to decide what property we would use. Taking a look first at the 5 log of x and the 4 log of y. Before I would subtract following order of operations, I would have to multiply first, specifically the 5 with the log of x and the 4 with the log of y. If I take a look at my properties, the last property involves multiplying a number with a logarithmic expression, k log base b of x. To handle the multiplication, I can take k and I can raise it as a power of x. So applying our power rule, 5 of log x is the same as log of x to the 5th, while 4 log of y is the same as log of y to the 4th. Next, I would try to subtract the two logs, following order of operations. How do we subtract logs? We can use the quotient rule of logarithms. That is log base b of x minus log base b of y equals log base b of x minus y. Now, since my bases are base 10, because remember when the base is not written, we are working with the common log, which is base 10. To write the difference as a single log, we're going to divide the inputs of the two logs. And the order does matter. Log x to the 5th minus log y to the 4th. Whatever's in the second log in the subtraction, that goes in the denominator. Whatever's in the first log for the subtraction goes in the numerator. 5 log of x minus 4 log of y equals log of x to the 5th over y to the 4th. Next, we're going to simplify 2 log base 4 of 3 plus 3 log base 4 of x minus 2 log base 4 of y minus log base 4 of 6. Just like in the previous example, we're going to handle the multiplication first. That is the 2 times log base 4 of 3, 3 log base 4 of x, and the 2 log base 4 of y. And we're going to handle that using the power rule for log. So 2 log base 4 of 3, applying the power rule, becomes log base 4 of 3 squared. 3 log base 4 of x becomes log base 4 of x cubed. 2 log base 4 of y becomes log base 4 of y squared. And our last log, because it didn't have a coefficient, will keep the same. Now, there's a couple different things I'm going to do to simplify next. First, we see the 3 squared. With the 3 squared, we can evaluate that. We know 3 squared is 9. And for the next one, notice how our last two logs have a negative sign. To make writing our final answer easier, I'm going to factor out the negative sign in those last two logs. So simplifying the 3 squared, log base 4 of 3 squared becomes log base 4 of 9. The log base 4 of x cubed stays the same. And now we're factoring out the negative 1 from our last two terms. And when we do, the negative log base 4 of y squared minus log base 4 of 6 becomes negative the quantity log base 4 of y squared plus log base 4 of 6. Now I can simplify the two additions. When we see for the first two terms and inside of our parentheses using our product rule. meaning when I add the two logs, I multiply their inputs. So log base 4 of 9 plus log base 4 of x cubed becomes log base 4 of 9x cubed. Log base 4 of y squared plus log base 4 of 6 becomes log base 4 of 6y squared. Now I still have the parentheses around the log base 4 of 6y squared. That's just to check later to see if I need them. Well, since I condensed the two logs to a single term, I can drop those out of parentheses. Now I'm in a scenario where I'm subtracting two logs. Now I can use the quotient rule to condense into a single log. To use quotient rule, when I subtract the two logs, I'm dividing the two inputs. So log base 4 of 9x cubed minus log base 4 of 6y squared equals log base 4 of 9x cubed divided by 6y squared. And the 9 over 6 we can reduce farther. And when we do reduce, we get log base 4 of 3x cubed over 2y squared. Remember, when you're trying to simplify many logs into a single log, use the order of operations to help you decide which are the three properties at the bottom you want to use. Also, be on the lookout for any simplification you can do as you go along. Next, we're going to completely expand log base 5 of 3,750 all over the cube root of x squared minus 1. What we mean by expand completely is we're going to rewrite our logarithm into many logs, and we're going to rewrite it so that way we can no longer apply any of our logarithmic properties. The way we decide which property to start off with is based off of reversing the order of operations of how we would simplify the input of our logarithm. If we look at 3,750 over the cube root of x squared minus 1, the last operation we would perform is the division. That tells me I should use the property of the logarithm that involves division, which here would be the quotient rule. And when we apply the quotient property, we get log base 5 of 3,750 minus log base 5 of the cube root of x squared minus 1. Now we're going to focus one log at a time and apply properties as we go. Now, immediately, it may not look like there's any properties that can be used on either log. 3,750 is just a number. We don't see multiplication, powers, or division. The cube root of x squared minus 1, we don't immediately see any powers. But if we look at the 3,750 farther, we can rewrite it as a product of primes. Off to the side, we'll make a factor tree, and from the factor tree, we can rewrite 3,750 as 2 times 3 squared times 5 cubed. As for the cube root of x squared minus 1, cube roots or nth roots in general can always be rewritten as exponents. So the cube root of x squared minus 1 can be rewritten as x squared minus 1 to the 1/3. Now, for the first log, we're taking the log of the product of three numbers. We can apply the product rule, and even though the product rule here states a product of two numbers, it can be applied to 3, 4, 5, or any number of numbers being multiplied together. We would just write each factor in its own log. So log base 5 of 2 times 3 squared times 5 cubed becomes log base 5 of 2 plus log base 5 of 3 squared plus log base 5 of 5 to the 3rd. As for our second log, we can now apply the power rule, which is our bottom rule there. And when we do, make sure you keep x squared minus 1 in parentheses, since x squared minus 1 is now the input to our logarithm. Now we'll check each log, see if there's anything more we can do to simplify. Log base 5 of 2 is as simplified as we can make it, since 2 is a prime number. But for log base 5 of 3 squared, we can apply the power rule to bring the 2 to the front. As for the log base 5 of 5 to the 3rd, we can apply the third property, log base b of b to the x equals x, and that would be equal to 3. As for our last logarithm, it may be tempting now to use power rule because we see the x squared. However, we're picking our properties based off of the last operation we performed if we follow order of operations. If we were to simplify x squared minus 1, the last expression we would do is subtraction. But there is no subtraction rule for logs in the sense of the log of a difference equals some sort of combination of logs. However, if we look closely, we can see that x squared minus 1 is factorable. And if we factor x squared minus 1, we get x minus 1 times x plus 1. Now we can apply the product rule to log base 5 of x minus 1 times x plus 1. However, be very careful. Because log base 5 of x minus 1 times x plus 1 is being multiplied by negative 1/3, we need to put grouping symbols of some kind around the log base 5 of x minus 1 plus log base 5 of x plus 1 to indicate that that sum has to be multiplied by negative 1/3 as well. Then we can distribute into negative 1/3, and we obtain log base 5 of 2 plus 2 log base 5 of 3 plus 3 minus 1/3 log base 5 of x minus 1 minus 1/3 log base 5 of x plus 1. From here, we are done expanding. Log base 5 of 2 and log base 5 of 3 are as simple as we can make them because 2 and 3 are prime. Can't factor them down any farther. And as stated before, there is no subtraction rule for logarithms, so log base 5 of x minus 1 is as simple as we can make it. And lastly, there is also no addition rule for logs, meaning that log base 5 of a sum cannot be rewritten in some way. So we've fully expanded our expression. Next, we're going to completely expand the natural log of the 5th root of 3 times x minus 4 times z plus 15 to the 10th all over y minus 12. Just like with the last example, we're going to use the logarithmic property based off of what our last operation would be if we were to simplify the input. Now, the last operation in this example would be that 5th root, which remember, 5th roots are just exponents. So I'd start off by using our power rule, treating our 5th root as a 1/5 power, and we get 1/5 times the natural log of 3 times x minus 4 times z plus 15 to the 10th all over y minus 12. Now, our last operation will be division, so we'll use the quotient rule. Now, our quotient rule is going to require us to make our one log into two logs that are being subtracted together. Since that result has to be multiplied by 1/5, I do need to put a set of parentheses. And we get 1/5 times the natural log of 3 times x minus 4 times z minus 15 to the 10th minus the natural log of y minus 12. Next, simplifying the first natural log, the last operation we would perform is the multiplication of the three numbers. So we'll use the product rule, putting each factor in its own natural log. And our first natural log would be rewritten as the natural log of 3 plus the natural log of x minus 4 plus the natural log of z minus 15 to the 10th. As for the last natural log, the natural log of y minus 12, our last operation we would perform to simplify a subtraction, and we don't have a subtraction rule. So it will remain as the natural log of y minus 12. Now if we check to see if there's any more properties we can use, natural log of 3 is as simple as I can make it. Natural log of x minus 4 is as simple as I can make it. But natural log of z minus 15 to the 10, I can use the power rule again to bring the 10 to the front. And our natural log of z minus 15 to the 10 can be rewritten as 10 times the natural log of z minus 15. And we already know our last log is as simple as we can write it. Now going through our logarithms to make sure everything is expanded fully. Natural log of 3, nothing more we can do. Natural log of x minus 4, nothing more we can do. Same thing goes for the natural log of z minus 15 and natural log of y minus 12. So we have fully expanded our logs. Now if we wanted to, we can distribute the 1/5 in, and we get 1/5 the natural log of 3 plus 1/5 the natural log of x minus 4 plus 2 times the natural log of z minus 15 minus 1/5 the natural log of y minus 2 minus the natural log of y minus 12. In this example, we want to evaluate the common log of 5 raised to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 power. If we go to Desmos, since this is the common log, the Desmos scientific calculator will be able to handle this log. So let's try typing it in. So we have log of 5 raised. Now let's type in our exponent. 1, 2, 3, 4. And without even typing the entire exponent, notice how it says undefined. The reason why it's saying undefined is when I type in the rest of my exponent, the way Desmos is going to want to evaluate this number is through the order of operations. So first I would want to do 5 raised to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, but it's too big of a number for Desmos to handle. And you can just see just by having 5 to the 123, we have 9 times 10 to the 85th power, which is a really big number. So how would we be able to evaluate this logarithm? Thanks to our power rule of logarithms, we can take this power and bring it to the front of the log. And now instead of trying to do 5 raised to this massive power, I can do this massive power times log of 5. So now let's type this into Desmos. So first we have the 1, 2, 3, 4, 5, 6, 7, 8, 9 times log of 5. Now because log of 5 will be irrational, going by Desmos' rounding, we get 862,925,923.4 as the approximate value of log of 5 raised to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 power. Without using these properties, we would not have been able to evaluate this value the way it's currently written with technology. So that is one of the uses of these properties, is they can turn really large numbers into really small numbers, which will allow technology to handle them. Next, we're going to use our properties of logarithms to help us evaluate the following expressions. Log base 3 of 27 to the 5th. If we were to follow order of operations, which your calculator will always follow, we would have to evaluate 27 to the 5th. Well, it turns out 27 to the 5th is a really large number. If you try to plug that into your calculator, you'll see that 27 to the 5th is about an 8-digit number. Some calculators start having trouble handling such large numbers. But thanks to our log properties, we can handle that 5th power, which makes the 27 to the 5th so large. If we use our power rule for logs, which is the last rule in our list, I can take the power of 5 and I can bring it out to the front of my log as a coefficient. So instead of having to worry about 27 to the 5th, now I just rewrote, so that way I don't have to worry about powers. Now I just have to worry about multiplication. Now we would evaluate the log base 3 of 27. So 3 to what power gives us 27? That would be 3, and 5 times 3 is 15. Next, we're going to evaluate log of 1 over 1,000. Now this problem is very similar to what we saw in example 3, where we were trying to evaluate log of 1 over 100. But this time we're going to use our properties of logarithms to help us rewrite it, so that way we don't have to guess and check so much. First, since I have log of 1 over 1,000, 1 over 1,000 represents division. So the first thing I'll do is use the quotient rule of logs to rewrite, so that way I don't have the division anymore. So log of 1 over 1,000 equals log of 1 minus log of 1,000. Log of 1 we can evaluate. We can either think 10 to what power gives us 1, or we can use the special property that log base b of 1 is always 0. Either way, log of 1 will be 0. Next, log of 1,000, 10 to what power is 1,000? Well, that would be the third power, because 10 to the third equals 1,000. And then finally, to finish, 0 minus 3 is negative 3. Next, we're going to evaluate log base 5 of the nth root of 5. Recall from our discussion in example 3, whenever we take the nth root of a number, that equals that number raised to the 1 over n power. So the first thing I would do in this problem is I'd rewrite that fourth root into an exponent. The fourth root of 5 equals 5 to the 1/4. Now I'm trying to evaluate log base 5 of 5 to the 1/4. Thanks to our third property, that will be equal to 1/4. Next, we're going to evaluate log base 6 of 2 to the 5th plus log base 6 of 3 to the 5th. Now, it does seem very tempting right now to try to evaluate each one individually, but I can't think of a power of 6 that'll give me 2 to the 5th, nor can I think of a power of 6 that would even just give me 2. So I wouldn't want to kick the 5 out using the power rule. And the same thing goes for log base 6 of 3 to the 5th. I can't think of a power of 6 that gives me 3, let alone 3 to the 5th. So directly evaluating or trying to use the power rule right now to make the number smaller doesn't seem to help too much. But notice that I'm adding 2 logs of the same base. I can try to at least simplify this and see after simplifying if there's anything I can do from there. Well, according to our fourth rule, if I add 2 logs together and they're the same base, I can multiply their inputs and write it as a single log. So log base 6 of 2 to the 5th plus log base 6 of 3 to the 5th can be condensed to log base 6 of 2 to the 5th times 3 to the 5th. The next thing that stands out is both of my exponents are 5, and I know that 2 times 3 equals 6. Fortunately, one of our properties of exponent is that if I'm multiplying a to the n and b to the n together, two numbers of different bases but the same exponent, I can multiply the bases and raise that product to the same power. In other words, a to the n times b to the n equals the product ab raised to the n. So applying that property, 2 to the 5th times 3 to the 5th is equal to 2 times 3 to the 5th, and 2 times 3 is 6. So now I'm trying to evaluate log base 6 of 6 to the 5th. I can use the third property, and we get 5. So log base 6 of 2 to the 5th plus log base 6 of 3 to the 5th equals 5. Before calculators were invented, scientists and mathematicians had to rely on tables in order to evaluate logarithms. In these tables, the value of certain logarithms would be given, but only for select inputs. The reason why we would only use select inputs rather than every possible input we could imagine is in order to reduce the writing. So as an example, we're given that log base b of x equals -3, log base b of y equals 2, and log base b of z equals 11. We want to figure out the value of log base b of xyz. Since xyz is not one of our known values, we need to use our properties in order to rewrite our log, so that way we can see the log base b of x, the log base b of y, and the log base b of z. Since we're taking the log of a product, then we can use our product rule on the right and rewrite log base b of xyz as log base b of x plus log base b of y plus log base b of z. Now that I have my log expanded, I can replace each of my logarithmic expressions with their given value. Log base b of x is -3, log base b of y is 2, and the log base b of z is 11. And if we do the arithmetic, we get 10. So log base b of xyz would equal 10. And thanks to these properties, I didn't have to know what log base b of xyz initially was. I could break it down into values that I did know. And the same thing goes for the second example, log base b of x squared y all over z. First, we'll start off by expanding the log. The first property we would use is the quotient rule, since we see division. In the first log, we'll use the product rule, and the first log would expand to log base b of x squared plus log base b of y. As for the log base b of z, that is a known value. It's as simple as we can make it as well, so we won't do anything to the log base b of z. Looking at the log base b of x squared, we can apply the power rule, bring that 2 out in front as a coefficient, and we have that log base b of x squared y over z equals 2 log base b of x plus log base b of y minus log base b of z. Since we know what log base b of x, log base b of y, and log base b of z are, we can plug in our values. Now with our values plugged in, we can do the arithmetic, and we get log base b of x squared y over z equals -15. Let's take a quick look at the first problem in example 6 with log base 3 of 63. Recall from the section where we first introduced logarithms that most scientific calculators can only handle base 10 and base e. But if we look at log base 3 of 63, that's neither base 10 or base e. Can we also think of 3 to what power will give us 63? Unfortunately, I can't think of a number that I would raise 3 to in order to give me 63. So what we need to do is figure out a way to rewrite our logarithm to involve bases of logs that we know how to use technology for. And this is where the change of base formula comes in. Let's suppose a and b are positive real numbers that are not 1, meaning a and b are valid possible bases for a logarithm. We're going to let m be positive, that way it can be an input into our logarithm. We'll be able to change our logarithmic expression of base b into a logarithmic expression of base a using the following formula. Log base b of m equals log base a of m divided by log base a of b. This formula is referred to as the change of base formula, since we're changing our logarithm of base b to logarithms of base a. Since most scientific calculators can only handle base 10 or base e, the best choice for a would be either 10 or e. Based off of your choice, our change of base formula will look one of two ways. If we choose common log base 10, then log base b of m would equal log m over log b. If you choose base e, then log base b of m would equal natural log of m over natural log of b. It does not matter which base you choose, since they will both give you the same result. Taking a look back at example 6, we can apply the change of base formula to log base 3 of 63. If we choose to write with the common log, we would have log of 63 over log of 3, and if we choose natural log, it would be natural log of 63 over 3. To illustrate that they both give you the same answer, let's go to Desmos. When we type in log of 63 divided by log of 3, we get about 3.7712. And notice that if we use natural log instead of log, we get the exact same answer for both. So it does not matter which you pick, you just need to use one variation of the change of base formula, either base 10 or base e, common log or natural log. Whichever one you choose, log base 3 of 63 will be approximately 3.7712. For log base 5 of 22, to use the change of base formula, we have to use either base 10 or base e. I'm going to pick base e, meaning I'm going to use the natural log. The reason why I'm picking the natural log is purely because I want to write one less letter. So natural log of 5 of 22, so log base 5 of 22 equals the natural log of 22 over the natural log of 5. Going into Desmos, if we type in the natural log of 22 divided by the natural log of 5 and round the 4 decimal places, we get 1.9206 as the approximate value of log base 5 of 22.